Hi, and welcome back to episode 3 of trying to solve some mathematical problems with OpenAI's Codex. We're on to project Euler number 3, the largest prime factor. So the prime factors of 13,195 are 5, 7, 13 and 29. What is the largest prime factor of a given number n? So if we have up to 10 test cases and we're given a number up to a trillion, find the largest prime factor of that number. And seeing as we're doing a few historical notes about the topics we're studying, I thought it might be interesting to add some for prime numbers. So this is really interesting. The Rind mathematical papyrus from 1550 BC, so I think this is a picture of it, very old, has Egyptian fraction expansions in different forms for prime and composite numbers. So they had obviously some concept of prime numbers going way, way back. Egyptians had very sophisticated mathematics. Often used to measure out different fields. I heard one reason they developed so much mathematics is that when the Nile flooded, it would wash away all the boundary markers to where people's fields were, and then when the floods receded and you wanted to go and plant your crops, you had to know how much space each person had. So it was really important to be able to go out and put all the boundary stones back such that the fields were the same size as they were before. And to do that, you had to calculate the size of the fields accurately. And to do that, you had to develop things like theorems for triangles and rectangles and circles and things in order to know how to measure these fields properly. And then it says the earliest surviving records of explicit study of prime numbers come from Euclid's Elements, which is an enormously famous mathematical treatise. It was completely standard in mathematical education all the way up until probably the 1950s or 60s. And he proved that there were infinitely many prime numbers, and he proved the fundamental theorem of arithmetic that all numbers are can be described as a multiple of prime factors. So if you take several prime factors and multiply them together, you get that number, and that set of prime factors is unique. And that's the fundamental theorem of arithmetic. And actually this question relies on that, because it's saying what is the largest prime factor. So there must be a unique set of prime factors which will have a largest value. And another interesting thing is he said you can prove how to construct a perfect number from a Mersenne prime, which is kind of amazing. So a Mersenne prime is one of the form 2 to the n minus 1 for some integer n. It's a special set of primes. And then a perfect number is a number which is the sum of its positive divisors. So that's kind of an amazing result for someone to prove in ancient Greece when they didn't even have Arabic numerals or Arabic Hindu numerals. And again, the sieve of Eratosthenes, you'll probably see that because that's probably one of the things the machine's going to use to try and solve this problem. And another thing I thought was really interesting is in 1000 AD, Ibn al-Haytham found Wilson's theorem, which is slightly odd that it's called Wilson's theorem and not Ibn al-Haytham's theorem, characterizing the prime numbers as the numbers n that evenly divide n minus 1 factorial plus 1, which is really interesting. And another one, Ibn al-Bana al-Marakushi, not sure if I pronounced that correctly, observed the sieve of Eratosthenes can be sped up by testing only the divisors up to the square root of the largest number to be tested. So if you think about a number, for it to have two factors, so two things which multiply to make that number, one of them must be smaller than or equal to the square root, and one of them must be larger than or equal to the square root. Because if they were both smaller than the square root, when you multiply them, you get something smaller than the number, which is too small. And if they're both bigger than the square root, then when you multiply them, the result is too big. And so you have to have one on either side, or they can be equal to the square root. And so that means you only have to test up to the square root, which just speeds things up a lot, which again I think we'll probably see in solving this problem. So we owe him a debt of gratitude for that work. And then again, Fibonacci, our friend from last episode, pops up, and then in Liber Abaci, that book from last time, he was the first to describe trial division for testing primality, again using only divisors up to the square root. So a lot of these techniques that we're going to use were discovered by these people a very long time ago. Okay, so we come to the OpenAI playground, and we have the problem description, as it said in the beginning, and let's run Codex on it. So it's come up with this algorithm. So it says start with I equals 2. And again, while I times I is less than or equal to n, so this is saying while I squared is less than n, so that means I is less than or equal to the square root of n. So that where those mathematicians found out that you only have to go up to the square root, we're using that piece of information here. And then what it's saying to do is it's saying when you start with the number n, divide it by I, right? Firstly it says check if I is a factor of n. Okay, and if it is, then divide n by I. Okay, so make n smaller. So that strips out that factor. So if 2, for example, is a factor of that number, it will divide it and strip that factor out. Okay, and then it says increase I and go forwards and try and find the next number and the next number. And hopefully the thing that's remaining at the end will be the largest factor that we're looking for. So let's take this over to the test bed and run the code. So sample test case, it works very well for the number 10. We come up with the largest factor is 5, so the prime factors of 10 are 2 and 5. And so yes, we have the largest one, which is 5. And for 17, 17 is a prime number, so its largest prime factor is 17, and we correctly did that. So well done. So let's submit the test cases, and we failed one. Okay, that's kind of weird. It seemed to do very happy for a lot of these, but it failed one. So one thing to wonder about with this algorithm is what happens if the number that is input is a power of 2. So for instance, if the number was 16, so let's test against some custom input. So I'll do one test case with the number 16. Okay, so let's run it on that. And our output is 1. And that's definitely wrong because 1 is not a prime number. And secondly, 1 is not the highest prime factor of 16. 2 is the highest prime factor of 16 because it's 2 to the power 4. But it's not done that. And that's part of why this algorithm is going wrong, is because it's saying, first step, strip out all the 2's, and what do you have left? Well, we have just 1, so that's not correct. And so let's say, okay, let's try and fix that by hand, just see if that was the only problem. So if n is 1, so if you're left with n equals 1, let's just assume that it was meant to be 2. Okay, so let's run that on the samples. Congratulations. So let's submit this. So this is if we fixed it by hand, and it still says it's wrong. So these test cases are hidden, so we can't see what the problem is, but it still says there's some other issue. So there must be something else wrong with this code where it doesn't quite work correctly. Okay, so let's delete that, and let's go back to the drawing board. Okay, so let's see, and I think maybe there's some philosophy developing about how to help Codex to understand the problem better. So it's saying, what is the largest prime factor of a given number n? It's asking the whole problem in one step, whereas maybe we can ask it in 2 steps. So we could say, make a list of all the prime factors of n. Okay, so that's the first step. So first get all the prime factors, and then print the largest member, the largest one. So we're saying we're breaking this problem down into 2 steps. First make the list, then print the largest one. And again, it's interesting that things like the sieve of Eratosthenes are going to come up. Okay, so let's see what it's doing now. So it says start with I equals 2 and a list of factors which is 0. Okay, so again, search only up to the square root. If n is divisible by I, okay, so what this is saying is if n modulo I equals 0, this will return false. So if 0 gives false, so it'll move on. But it says if this is anything other than 0, just iterate I. So just move upwards, check next thing, it wasn't divisible by I. But if it is divisible by I, then divide n by I, right, and append the factors to I. And we know we've got a factor already, okay? And then when you're done, if n is greater than 1, then append n to the factors. So let's see if this is any better. I'm wondering if there is a problem here, because it's only testing each prime once, but let's see whether it works. It does! So there we go, congratulations. So I think that was quite interesting, that somehow giving the AI the problem in 2 steps really helped it to sieve out all of the factors first, and then, well, it wasn't actually using a prime sieve at this point, but to make the list of factors first and then just print the maximum of those values was much easier for it. Alright, thanks for watching. That's 3 problems down. On to the next one.